for the ECE Distinguished Visitor Program. Through a generous grant provided to the institute by one of our alumna, Mrs. Nirmala J. Pullur. So she has given some other endowments and donations to the institute, and specifically for this purpose, especially with all of us coming after this pandemic period where most of the talks have been online and there were hardly any interactions. So she basically suggested that we have very distinguished speakers come over and have a interaction with the researchers in the institute, and facilitated it through this grant. And we have Professor Athina Petropulu who will be giving this talk, and I now request Professor Hari to introduce the speaker, but before that I wish to thank her for being here with us and agreeing to share this and include this in her itinerary to give this particular talk here, which is of course planned earlier, and we were able to basically include this as well as one of the first talks, in such a way that we could inaugurate this program quick enough. As a matter of fact, this particular donation thing came in the last couple of months or so, right? I think just even later than that. So we will certainly have several such talks, and I look forward to all the the students and other colleagues from here joining us. The plan is to have two talks, two visitors in a year, and they will spend some time in the institute and elsewhere in the country as they visit under this program. So I may now request Professor Hari to introduce the speaker so that we can get started with the first talk.
Okay. Good afternoon, everyone. Thank you for coming, and welcome to the inaugural talk of the ECE-IISc Distinguished Visitor Program. So I'm very happy to introduce Professor Athina Petropulu. She's a distinguished professor at the ECE department at Rutgers, having served as chair of the department during 2010 to 16. Prior to joining Rutgers, she was a professor at Drexel University from 1992 to 2010. She has held visiting scholar appointments at Supelec, Princeton University, and University of Southern California. Her research interests span the area of statistical signal processing, wireless communication, signal processing, networking, physical layer security, and radar signal processing, which only means that signal processing is everywhere. And that is what we would like you to appreciate. And any strength in signal processing, you can do anything. Her research has been funded by NSF, Office of Naval Research, US Army, the NIH, Whitaker Foundation, Lockheed Martin, and Raytheon. She's a fellow of IEEE and the American Association for the Advancement of Science. She is currently the president of IEEE Signal Processing Society since 2022, and has served as editor-in-chief of the IEEE Transactions on Signal Processing, and has been the vice president conferences on the of the Signal Processing Society. She also has organized ICASP and many other workshops, but most recently she has initiated a very important series of workshops called Progress, which is basically to promote diversity. And she is a champion of women empowerment and diversity and inclusion. She has been recipient of many awards, including the Signal Processing Magazine Best Paper Award, the Young Author Best Paper Award of her student, and from AESS, the Barry Carlton Best Paper Award recently, and the 2022 IEEE Censored Multi-Channel Signal Processing Workshop Best Student Paper Award for her student. So apart from all the bio, I would like to say that I had the great privilege to work with her on the Board of Governors for the last 5 years. And she has been a very energetic, tireless Signal Processing Society volunteer, assuming a lot of positions and ensuring that there's a lot of representation of volunteers across the globe on various initiatives, and extremely committed and wonderful human being. Thank you, Athina.
Thank you, Professor Hari, for the introduction. I really appreciate the opportunity to be here and appreciate the efforts that you put in organizing so many events that I participated during my visit. So the privilege was all mine to serve the Signal Processing Society alongside Dr. Hari, who was an exemplary VP membership. He started a lot of initiatives for the Signal Processing Society. So today I will talk about my work, my group's work on dual function radar communication systems. And this is part of the PhD work of my student Zhaoyi Su, and his work supported by the National Science Foundation of the US. So the talk will has two parts. I will provide some motivation why we need such systems, dual function radar communication systems. I will mention the challenges and the open problems, and then I will present an approach that we recently proposed that will appear in the IEEE transaction signal processing probably in a couple of months, and which is an OFDM-based DFRC system that is bandwidth efficient. And then I will discuss efficient architectures for DFRC systems. So what is the motivation behind dual function radar communication systems? So 6G systems, or next generation systems, are envisioned to have communication, high rate communication ability, and also sensing capability, high resolution sensing capability. So if you look at future network vehicles, you want vehicle-to-vehicle communication, also vehicle-to side road infrastructure communication, and also a lot of sensing, because vehicles navigate using radar. So vehicle-to-vehicle communication would require, for example, one vehicle should be able to communicate with other vehicles the readings of its sensors. If it has radar sensors and senses obstacles, it should be able to communicate this information to other vehicles, for example, vehicles following. And by doing that, it enhances the visual horizon of the other vehicle. And this improves driving safety. But this requires high-rate information to be communicated. It's not possible given the existing capabilities. It also requires high sensing resolution. It needs to be able to identify obstacles with very high resolution. So you could do that having two systems, one that would do the communication, another that could do the sensing. But then you would need more hardware. If every car on the road would have two such devices, these devices will create a lot of interference. So there is a lot of interest in designing a single system out of the same hardware platform that can do both sensing and communication. And of course, to achieve high rate communications, you have to use high frequencies. Also, the sensing system in order to achieve high range resolution. It needs a lot of bandwidth, which means it has to operate in high frequencies. So you have frequency convergence between communication and radar systems. So using this high frequency and hardware, also the way with modern technology, radar systems and communication systems have similar RF radio frequency front-end architectures. So here you have hardware convergence and frequency convergence between the two systems, which means that you should be able to integrate the two functions in one device. So a lot of interest in integrated sensing communication systems these days. And a subclass of such systems are the dual function radar communication systems. So how do you integrate the two systems? You can assign, let's say, some of the frequency spectrum for sensing, some for communications, but when you do that, you don't use the entire bandwidth for communications or the entire bandwidth for sensing. So you don't fully exploit the available bandwidth. And of course, if you don't use the full bandwidth for communications, you don't achieve the highest possible communication rate. So you could integrate the two systems, let's say if you use multiple antennas, to use some antennas for sensing, some antennas for communications. But again, if you use a smaller number of the available antennas for sensing, you cannot design, you don't have enough degrees of freedom to design nice beams. The same for the communication system. So ideally, you would like to use as many antennas as possible. So DFRC, dual function radar communication systems, use a single waveform to both sense targets and convey communication information. So in that sense, they are bandwidth efficient because they fully use the available bandwidth, both for sensing and communication. So in this talk, I will discuss dual function radar communication systems. As I said, it's a subclass of integrated radar communication systems. So now you have one waveform that you're going to transmit. Suppose that you start with a radar waveform. How are you going to embed communication information in this radar waveform? There are various approaches that have been tried in the past. For example, you can embed information in, we can embed information in the side lobes, in the face of the side lobes. Or you can embed information in the way the waveforms that you transmit are coupled with antennas. But these are not high rate, they do not achieve high communication rate. You cannot send a lot of communication information using these approaches. There has been a lot of interest in OFDM waveforms. OFDM waveforms are known to achieve very high communication rate. So there has been a lot of interest in exploring the radar properties of those waveforms. And there have been a lot of works that I cite here. The open problem in those works is that they do not achieve full bandwidth utilization because of the way they assign subcarriers to transmit antennas. So in previous work, they assigned one subcarrier to its transmit antenna. What I'm going to present is our approach that exploits all available bandwidth by allowing antennas to transmit on multiple subcarriers. When antennas transmit on multiple subcarriers, then there is coupling in the radar echo, the target echo that you receive, there is coupling between the transmitted symbols and the radar parameters. And it's more complicated to extract target information. So I'm going to present a method that untangle this information from the radar echoes. Another problem with allowing all antennas to transmit on all subcarriers is the loss of orthogonality of transmit waveforms. The transmit waveforms cannot separate it at the receiver to formulate a virtual array. A virtual array is a well-known way to improve the resolution, target resolution. So I will explain how, in our approach, we can still formulate a virtual array while using most of the subcarriers in a shared fashion. So the work that I will present, you can find preprint on that link. It's going to be a DFRC system that transmits OFDM waveforms. It's going to be a monostatic MIMO radar system. And the subcarriers can be used in a shared fashion or in a private fashion. This means that most of the subcarriers will be used in a shared fashion. The antennas can transmit on all of the on those subcarriers. And a small group of subcarriers will be assigned exclusively to transmit antennas. So each transmit antenna will have one private subcarrier, and the rest will be shared subcarriers. So I will present a computationally efficient method to extract target parameters by first looking at the shared subcarriers where there is coupling. So I will I will present a computationally simple method to extract target information from the shared subcarriers. And this will be low resolution target estimation. Then I will explain how I can use the private subcarriers to fine-tune that information and obtain high resolution target estimation. So the system that I will present will have beamforming capabilities. So there will be waveform pre-coding at the transmitter, and the pre-coded waveform will be optimally designed so that I can achieve desired pattern, both for the radar and the communication operations. So the design will meet a joint sensing communication performance metric. So let's consider a two-antenna system. This is one antenna, and this is another antenna. The data are separate. The data that I want to transmit are separated into blocks, and one block is provided to the first antenna, the second to the second antenna. I have an OFDM system with NS subcarrier, so OFDM modulation will be performed by each antenna. But before I do that, I use this pre-coding matrix that multiplexes the streams of the two antennas. So I will explain how I will design this matrix in order to achieve a joint sensing communication metric. So typical OFDM modulation in each antenna, I will perform an inverse DFT, add a cyclic prefix, and then send the data through the channel. So D are the symbols that I will be transmitting from each antenna. And each symbol at the transmitter is denoted by the transmit antenna index N, the subcarrier index I, and the OFDM symbol mu. And at the receiver, this is a collocated system. So the receiver knows the symbols that have been transmitted. The receiver will perform OFDM demodulation, and these are the demodulated symbols. So each demodulated symbol DR is indexed by the receive antenna index, the subcarrier I, and the OFDM symbol mu. So I will assume that I have uniform linear arrays at the receiver and the transmitter. And I have NT transmit antennas and an R receive antennas. And G sub T and G sub R are the spacing at the receive and transmit and receive arrays. Suppose that I have K targets at angles theta K, range Rk, and Doppler frequency F sub D sub K. So these are the parameters that I'm interested in estimating based on the received echoes. Each antenna transmits an OFDM symbol with signal, which means that the transmitted signal on the ith subcarrier by the nth antenna can be expressed like this, like standard OFDM modulation. So the signal will propagate and find the targets, and it will be reflected back. And this is the signal that the mth antenna will receive on the ith subcarrier. So because there are K targets, it will receive the superposition of K terms. Each term will be the reflection of the transmitted signals because NT antennas transmit on the ith subcarrier. It's going to be a reflection of NT terms, and each term will be the transmitted signal delayed by this quantity. Beta sub K is the target reflection, the kth target reflection. And the delay is directly related to the range of the target and the angle of the target. So out of this received signal, I'm interested in the angle of the target, the range of the target, and the Doppler of the target. If I look at if I is the shared subcarrier, as I said, we have a summation that contains NT terms. NT is the number of antennas that transmitted on that subcarrier. If only one antenna had transmitted on that subcarrier, then this summation would not exist, would only have one term. And it would have been easy to estimate the target parameters. But because this summation exists, it complicates things. Still, we can find the phases if we notice that this complicated summation can be rewritten in this form. It's going to be summation of K terms, and inside each term has this quantity here. Let me put it by A, times e to the j omega m, where the omega contains the terms shown by red here. So the omega basically depends on the angles of the target and the system parameters, like the spacing of the transmit array. And A will contain everything else. So A will contain symbols, will contain ranges, will contain Doppler frequencies. So if I look at this dr as a function of m, let's freeze everything else. If you look at it as a function of m, then it's a summation of K terms, some constant that does not depend on m, times e to the j omega m, where we vary m. M is the index over the receive antenna. If we have NR receive antennas, is the sum, or we have NR samples here of that term. And this looks like a summation of K complex sinusoids, where omega is the frequency of its complex sinusoid, right? And the frequency directly depends on the angles of the targets. So how do we estimate frequencies? This looks like a discrete time sinusoid, if you view m as time, right? And omega is frequency. To estimate the frequency, if you take a discrete Fourier transform, you will see peaks at those frequencies. So the location of those frequencies can directly give you the angles of the targets. So by taking a DFT along the receive array, you will get target angle information. Of course, when you do that, your resolution, your angle resolution depends on the size of the DFT that you obtain, right? So if your receive array is small, you may not have very good angle resolution. We will refer to those angle estimates as coarse angle estimates, and I will show you how we can improve the resolution of those estimates in a little bit. For the moment, we can find the angles by finding these frequencies, and then we can go back to these terms that, if you see from in here, can be expressed as a term that I have already computed based on the angles, and a summation that represents terms that fall in this angle bin, the theta k angle bin. And this term contains the ranges of those targets and the Doppler frequencies of those targets. So I have found the angles, and in each angle bin, I have such an expression that contains the information of the ranges and the Doppler of the targets that fall in that angle bin. This term contains known terms. So if I look at this expression as function of I is the subcarrier index. This contains known terms. So in theory, I could compute this term and divide side by side, and then the rest would give me a summation where the subcarrier index only appears here. So this would look like a summation of complex sinusoid whose frequencies depends on range, right? But in general, it's not a good idea to divide, because if you divide, you end up with zeros, and the performance is very bad. So instead of dividing, we can see that what we have here is basically this quantity modulated, this is a modulation term, and the exponent here depends on range. So if you use the modulation property of the DFT, if I take a DFT along the I direction, what I will get is the DFT of this term shifted by these terms for all k's, right? So if I get the DFT shifted by these terms, I can use cross-correlation operations to find the amount of shifts that will give me the ranges. And then once I find the ranges, I can look at this expression again now as a function of mu, which is the symbol index. And then I will have a summation with respect to, if I vary mu, mu is the FDM symbol. If I take a DFT across mu, I will get the Doppler frequencies, which will give me the speed of the target. So to summarize, if we look at this graph, where here is the receive antenna index, and this is the subcarrier index. If I take a DFT along the first subcarrier, along the receive array, I will see peaks, and the peaks, the location of the peaks, will give me the angles of the targets. I can do that on all subcarriers, right? Same idea. So I will use frequency diversity provided by OFDM waveforms to find these peaks and then average out, and this will give me angle estimates, good angle estimates with high probability. And then I will do cross-correlation operations along the peaks of those angles, and this will give me peaks that will tell me where the ranges are. And then I will do a DFT along those ranges for different OFDM symbols, and that will give me the Doppler frequencies. So this is the idea in the proposed approach. Now, how can I improve the resolution of the angles? As I said, the resolution depends on the size of the receive array, and maybe I can do better than that. Suppose that I do not allow antennas to use all subcarriers in a shared fashion, but I reserve a small number of subcarriers, anywhere from 1 up to equal to the number of transmit antennas, And those subcarriers will be used by antennas in an exclusive fashion. For example, if this is the transmit antenna index and this is the subcarrier index, along the first subcarrier, only the first antenna transmit. Along the third subcarrier, only the third antenna transmit, and so on. Along the second subcarrier, all antennas can transmit. So the second subcarrier is shared, the fourth subcarrier is shared, but the first and the third are private. So if these private subcarriers will help me formulate a virtual array and see how this can be done. So if I look on the ith private subcarrier, I have k terms that look like this. So I have k terms, and this is like you can think of this as a scalar constant that depends on the kth target. It contains the Doppler frequency, the angle, and the range. And this is a vector that looks like a steering vector along direction theta k, but it also depends on the range of the target along direction theta k. Suppose that I stack all these vectors together to make a longer vector, z tilde, using all private subcarriers. Then I can rewrite this in a matrix form. So I can write this as a matrix phi times the vector beta. The matrix phi, the columns of the matrix phi, will be basically these vectors, these steering vectors that depend on angle and range. And the vector beta will have as elements these scalars, right, that contain range, angle, and Doppler information. Now, this looks like a virtual array. If you look at the real array, it has NR antennas, but this vector now has size M times NR. M is the number of private subcarriers that I stacked up here to create this vector. So this is already an M times the number of receive antennas long array. So it's a virtual array. Should provide higher resolution of angles. Now, how can we obtain angle estimation based on this equation? So to construct this matrix, I need to know, looks like I need to know the target angles. So instead of this knowledge, I can discretize the angle space. I can and construct a much larger problem for all possible angles, where beta basically is a much longer vector that has mostly zeros except non-zero elements at the grid points corresponding to targets. However, if I do that, if I discretize the entire phase space, I should also discretize the entire range space to formulate this matrix, because the columns of this matrix also depend on range. In order to avoid discretizing the entire space and creating a very long vector, so if I did that, that problem would be extremely difficult to solve. I can use the knowledge that I have obtained based on the shared subcarriers. I already have some low resolution angle estimates. So instead of discretizing the entire space, I can use the low resolution angle estimates that I have and discretize the space around those angles. I can do the same using the ranges that I have already found. So if I do that, then I can formulate a much smaller dimension problem here. And then I would solve for beta. If I solve for beta, the non-zero elements of beta will tell me where the angles are on the grid space, on the angle grid. Another good thing when I use the available information to construct this problem is that I guarantee that this problem will be sparse, because if I focus in a small region of space, then this region of space will be sparse. Only a small number of targets will fall in the same range bin, let's say, in closely spaced frequency bins. So this will be a sparse problem, and I can use sparse signal recovery methods to estimate beta. For example, suppose that we have 2 transmit antennas and 2 private subcarriers, and I have 4 receive antennas. I will look at those private subcarriers and create those vectors, put them together to create a longer vector. So it's an 8x1 vector that corresponds to an 8x1 virtual array. And this is my phi matrix that is constructed by discretizing the angle space around the estimated frequencies. And this is, and to construct these vectors, I used the estimated ranges. Now this is a sparse vector. The non-zero elements are related to one column of this matrix, and the column of this matrix is directly related to angle and range. So if I apply sparse signal recovery methods to estimate this vector, the location of the non-zero elements will give me refined angle and range estimates. So although I will use like low resolution estimates to discretize the space, when I solve this, I will get much higher resolution angle estimates. So we are going to, we have this scheme. This is the receive antenna index. This is the subcarrier index. The yellow are the shared subcarriers. I will use all subcarriers and apply DFT operations to obtain angle, and then cross-correlation operations to obtain range. And then I will use the range and angle estimation to formulate a sparse signal recovery problem. And this problem will give me updated fine-tuned angles. I can use these angles to refine my range estimate. And turns out that I can iterate this a couple of times to obtain high resolution estimates. So I should have said that in order to formulate this virtual array, I need the information received on the private subcarriers, right, to construct this virtual array. If we look at the communication receiver across the receive antennas on the ith subcarrier, we have this expression is standard OFDM communication receiver. So HI is the channel frequency response along the ith subcarrier, and DI is the vector of symbols transmitted by all antennas on the ith subcarrier, and UI is noise. If the channel matrix is known, which can be known using pilot symbols, then I can recover the transmitted vector using least squares, using standard OFDM schemes. So for fastest communication speed, I will have all antennas, I will have all subcarriers used in a shared fashion. In this case, I can achieve communication rate NT, the number of transmit antennas, times the number of subcarriers. So I can transmit NT times NS symbols in each channel use. In this case, the angular resolution is the number is proportional to the number of receive antennas. Now, if I want to improve the angular resolution, I will use a small number of private subcarriers, let's say M, where M is anywhere from 1 up to NT, the number of transmit antennas. Based on that, those private subcarriers, I will formulate a virtual array, and based on that, I will improve the angular resolution by M. So my angular resolution will be M times NR. And when I do that, I will reduce the rate by a small amount, so my rate will be equal to this. So in OFDM symbols, we need to estimate the channel, so we use pilots. So the private subcarriers, in this case, could be the subcarriers that are used to estimate the channel. So it could be the subcarriers that transmit pilots for channel estimation. Now, how do we design the pre-coding matrix P? One could use various criteria. Here we use a criterion that minimizes the beam pattern error with respect to some optimal beam pattern B. So this is the beam pattern, and this is B, some desired beam pattern, subject to meeting an SNR at the communication receiver. So we can solve this optimization problem to design the pre-coding matrix P. I can give you more details if you are interested later on. So some simulation results. We have 16 transmit antennas and 32 receive antennas. And we consider OFDM system with carrier frequency 24 gigahertz and 512 subcarriers. And in this case, we are interested in formulating a narrow beam, shown by the red line here, in that direction, because our communication receiver is here. And we want to formulate a wider beam, shown by the red line here, in these directions, that potentially contain targets. So using the optimization problem that I showed you before, we applied the Adams optimizer, which is an iterative approach. We obtained the blue line. So the blue line shows the beam pattern that we could achieve using the criterion that I just showed you. And this shows how the error function behaves per iteration. It converges very fast. And this shows how the SNR behaves per iteration at the communication receiver. And you can see that the SNR depends on the number of transmit antennas. The more antennas I used at the transmitter, the slower I reach convergence, but it's the highest SNR that I achieve upon convergence. A sensing example now. Suppose that I have 8 transmit antennas and 32 receive antennas, and 8 subcarriers are used as private out of the 512. And I consider a scenario where I have 4 targets, 2 of them fall in the same angle bin, and the other 2 in different angle bins. And these are the ranges of the targets and the velocities of the targets. And here I show range per angle. The ground truth is shown by the blue circles, shows the ranges and the angles of the targets. And the red stars show what I get if I apply the DFT-based estimation of the targets. So you can see that I only recover 2 angle bins. I have 3 different angle bins here. I only get 2 based on the DFT approach because I don't have enough resolution to resolve the 2 angles here. So based on those, I estimate ranges. You can see that the ranges that I estimate using the cross-correlation operation approach are actually correct. Those ranges are good because I use all the bandwidth. So the ranges have high resolution. So if I use those ranges and discretize the angle space across close to the estimated angles, I get what is shown here by the crosses, which are correct angles and ranges. So using the sparse signal recovery, I can estimate the correct angles. And this is another example where I show here again range and angle. I have a scenario with 4 targets, and if I use DFT estimation, I only estimate 1 angle, and if I look inside this angle, I have 2 targets. I find 2 ranges. The blue stars indicate the correct information, range and angle. So if I use these two ranges and the one angle to formulate a sparse signal recovery problem, I will get what is shown here. I will get the 4 angles correctly. And if I use the 4 angles, I can set up, I can use the cross-correlation operations to find the ranges. I find the correct range and angle information at the next step. This is how the range estimation is based on cross-correlation operations. So this is one example where the ranges are very closely spaced. So if I go through the low-resolution approach, I find the low-resolution angles and then use cross-correlation to find the ranges. I'm missing some targets. So the dotted line here show the ground truth for the ranges, but the cross-correlation approach give me one peak, right? Still, if I formulate the sparse signal recovery problem based on this single range, and I discretize the range space around it, I will be able to obtain the correct range information. So setting up this sparse signal recovery problem does significantly improve the resolution of the targets. So in this example, I have 6 random point targets, and I do Monte Carlo simulations, and I want to see how the target estimation performance behaves versus the number of private subcarriers. So this is target estimation, this is number of private subcarriers, and this is the communication rate loss. As I'm using more private subcarriers, I'm losing communication rate. So you can see that as I keep increasing the number of private subcarriers, the sensing performance increases, right? The target detection probability increases. But I'm losing communication performance. So you can see that for each private subcarrier that I'm using, I'm losing about 6 megabits per second communication rate. But it turns out that I don't need to use that many private subcarriers. If I use 3 in this scenario, I have already achieved the maximum possible sensing performance at a small communication rate loss. And this shows the mean square error of angle estimation. This is before I do the sparse signal recovery based estimation using the DFT operations, and this after I formulate and solve the sparse signal recovery problem. You can see dramatic improvement in estimation performance. And this is the mean square error for range and Doppler estimation. This is the bit error, the communication bit error versus SNR. So the examples that I showed you were at 20 dB signal to noise ratio. And here I show how the bit error rate behaves as the number of antennas increases. So for the simulation example that I used before, for 16 transmit antennas, the maximum bit rate of the system was 3.2 gigabits per second. And the loss of bit rate due to the use of private subcarriers is 6 megabits per second. Now, we also considered ways to recover some of the loss because of the use of private subcarriers. And in particular, we exploited the possible permutations of private subcarriers among the available subcarriers. In particular, so embedding information, we consider embedding information in these permutations. For example, there are NS choose M ways to choose M subcarriers to be used as private out of NS total subcarriers. And there are NT choose M ways to choose M antennas to be assigned private subcarriers. And there are M factorial pairings between private subcarriers and antennas. So log2 based this many bits we can use to convey information in each OFDM symbol. So in addition to the symbols that we will transmit via OFDM, by pairing subcarriers to antennas, private subcarriers to antennas, we can be transmitting additional information. Of course, in order for this information to be useful, we need a simple way to be able to extract it at the communication receiver. And for that, we can use the one-sparse property of the private subcarriers. For example, if we look at the receive vector along the ith subcarrier at all antennas, we have this equation that I already mentioned. This is the frequency channel matrix, and this is the vector of the symbols transmitted on the ith subcarrier by all antennas. If this is the private subcarrier, then only one antenna has transmitted on this subcarrier. So this is a one sparse vector. And basically, what I receive is if the nth antenna transmitted on that subcarrier, then what I get is the nth column of this matrix times the symbol that was transmitted, plus 1. So based on the received vector, I need to determine which column produced this observation, right? And you can do that by solving a one sparse signal recovery problem based on this, but that would involve a lot of complexity. So we proposed a computationally simple approach to find that column that goes as follows. So take this matrix and divide it into two components and project the received vector on both matrices, on the subspaces spanned by the columns of these matrices. When you do that, it turns out that only one submatrix will, only one subspace will preserve the length of the received signal. So you can go to that matrix, subdivide it again, project, keep subdividing, and in the end, you will find the column of the matrix that gave rise to your observation. If the given subcarrier is shared at some point of the above process, then Ri would lie in both subspaces, and then you know that this was a shared subcarrier. So using this binary search approach, you can identify which subcarriers are private at the receiver. And once you find that, you also know what was the antenna that submitted on that private subcarrier. So here you have the pairings that contains the additional information. Of course, to do that, you need the communication receiver needs to have more than NT/2 antennas. NT is the number of transmit antennas in order to guarantee independence between the columns of its channel submatrix. So we conducted experiments for the interest of time. Maybe I will skip the results. So for these parameters here, the communication rate of the system was 7.55 megabits per second. Using private subcarriers result in a rate loss of 74.4 megabits per second for each private subcarrier, but pairing the permutation of private subcarriers and antennas, we can recover 11 megabits per second. Now, I'd like to take a couple of minutes to discuss the reduction of hardware cost. So I use MIMO radar as the transmitter. MIMO radar means that I use multiple RF fronts. Its antenna has an RF front and transmits a waveform, right? So this involves high cost, so there is a lot of interest in reducing the cost of a MIMO radar, and that's why people have been looking at hybrid structures. And a hybrid structure is you connect each RF chain to a network of antennas. These antennas, basically, each one multiplies the signal by an e to the j term, by a unit modulus scalar. And by changing those weights, the phases of these terms, you can formulate a nice beam pattern that would be close to what you could have achieved using more RF fronts. The problem is that because these are unit modulus weights, you cannot control their amplitude, right? If you were able to control their amplitude, then you would be able to, you would have more degrees of freedom to design a much better beam pattern. But to do that, you would need like RF chains. Next, I'm going to show you how you can do it without RF chains. So let's consider the case of a single RF chain connected to these antennas. The antennas multiplied the signal that comes out of the RF chain with an e to the j phi term, and then transmit it. And by optimally designing the weights, the phases of these terms, you can make the antenna, the beam pattern, focus in a specific direction. Because those are e to the j phase terms, you don't have good control of the side lobes of the beam pattern that you will design based on such a structure. Now, let's consider this structure instead. So take the signal after it's multiplied by e to the j phi term and add them up, and then transmit them through the antenna. When you do that, e to the j phi 1 plus e to the j phi 2 gives you a term that has both amplitude and phase, right? And you can control both the amplitude and the phase of this term to design a beam pattern. So this structure gives you more degrees of freedom at the expense of using maybe more antennas, but these antennas are, these multiplication components here are very simple. They don't involve significant cost, but they allow you to create, they give you more degrees of freedom to design the beam pattern. For example, you can design the weights here that are of this form, and maybe the phases are discretized, so that you minimize the error with respect to some ideal weight. For example, the ideal weight could be the MVDR beamformer, minimum variance beamformer. So in this case, this example, you have targets that fall in this direction, and you have scatterers of no interest that are indicated by these dotted lines. If you use the phased array, one RF front and analog processing after that, you will get what is shown here by the yellow line. The yellow line gives you a nice peak around the location of the target, but does not allow you to avoid the scatterers. So you send a lot of power to those scatterers, and those scatterers will give you back returns that are of no interest to you. They represent clutter. So how can you reduce that clutter? Well, if you use that approach with a double phase shifters, you can design what is shown by the red line. The red line gives you a nice peak around the target, but gives you nulls around the scatterers, right? You're trying to emulate the MVDR beamformer, that is, the weight is given by this expression, that specifically tries to achieve nulls at certain angles where there are the scatterers. Of course, if you used two RF fronts in this scenario, you would achieve what is shown here by the blue line, that achieves deeper nulls at the scatterers, but in this case, this scheme would involve a much higher complexity. So to conclude, I present the wideband OFDM DFRC system that uses subcarriers in a shared fashion and as a result achieves a high communication rate. I showed you how we can trade off some of this communication rate to improve the sensing performance via the use of private subcarriers. And I show you how we can embed additional information in the OFDM waveform based on the pairing of private subcarriers and transmit antennas, and how we can improve the architecture, reduce the cost of the architecture for a DFRC system. So right now we're looking into security related to DFRC systems. In particular, when you transmit a waveform that is meant for a communication receiver and you expect with the same waveform to get reflections from targets, if the target is an eavesdropper, they may be able to extract the information that is meant for the communication receiver, right? Okay, you can use coding, but an eavesdropper, if they have enough computational resources, they can break the code. So what can you do to prevent an eavesdropper from intercepting the message that you're sending? So we are considering various security, physical layer security approaches for DFRC systems. And thank you very much for your attention. Yes.
Thanks for the great talk, ma'am. In the sparse signal recovery problem, it is assumed that targets would fall on the grid points.
Yes.
So it's not the general case that sources won't fall on the grid. There would be performance loss if the targets won't fall on the grid.
Right. Yes, indeed. This is a problem when you use grid-based approaches. Right? You can discretize the space finer, but when you do that, the columns of the sensing matrix are correlated, and then the sparse signal recovery does not work. So this is indeed a limitation of sparse signal recovery methods.
So following up that, can we solve such problems without grid at all? I mean, assuming the without grid approach.
Without a grid?
Yes.
Possibly, yes. There are gridless approaches. There is literature for gridless approaches for solving sparse signal recovery problems. So maybe one could use those.
I have a couple of questions, but I would like to put them as one question. You see, you have not explained your use case, because the ranges you are reporting only are in meters. That is only a terminal phase kind of action. And you have not mentioned whether you have done any cyclo, you have avoided cyclo, how you have avoided that, because the slide you showed had no cyclones at all in that. And is it down to their experiment?
Okay, this is a good point. So we are looking into systems that could be used for automotive radar systems. So those are gigahertz frequencies. Those frequencies do not travel very far. So we're talking about small distances, right? Those frequencies are for a particular scenario.
Paper which has done a virtual array by first choosing a signal from each antenna and then combining a pneumocircumferential fairly and if you compare the results of that with your approach, was not like
Yes, the idea here.
From UK.
Right. I mean, there is a lot of literature on this, but the idea here is to use the same waveform for both sensing and communication at those high frequencies, right? And you want to achieve a high communication rate. So there are multiple.
It looks interesting, but
Yes, you're right. So I skipped a slide. So I'm interested in autonomous systems. Autonomous systems, like automotive radar, work in gigahertz range. And communication systems use millimeter wave frequencies in order to achieve high communication rates. So I'm interested in that scenario. And everything that I explain is for that scenario. Thank you. Yes.
I have a question. So this is with reference to the embedding of information in the pairing of transmit antennas and private subcarriers. When you do this embedding, there is also an issue of performance.
Yes.
To what extent does the performance degrade? Because this information may not be easily recoverable.
Yes,
the second
exactly.
part to that question is there are 3 different kinds of embeddings that you mentioned. And the bits that you embed in each of those parts may have different probability of errors.
Right.
So is that an issue, or is there a way by which you can equalize them? How would you exploit
So
those
this
things?
is a good question, and one should look into this. We haven't looked into this. But regarding the performance, I had the graph here. That shows how the runtime and the detection probability behave versus the number of receive antennas. In order to achieve, to be able to say that the columns of that matrix are independent and the projections to work, I need to have enough receive antennas at the communication receiver. So you can see here that in this scenario I have 32 transmit antennas, and the detection performance starts picking up after I get more than 30 antennas at the communication receiver. And then it picks up very fast. So it picks up very fast. This is the runtime as the number of antennas increases. So the runtime, it's simple, it's a binary method, but I do a projection. So at some point, this projection matrix becomes large as I increase the number of receive antennas, and MATLAB, this is MATLAB-based result, switches and uses a different algorithm, and the computational performance, the runtime increases significantly. So this says that maybe up to here, this tells me how many transmit antennas I need to use to achieve high enough detection probability without increasing the complexity. So we have done some simulation studies, but of course more work is needed. This was only a
Yes. Yeah, thank you for thank you for an excellent talk. I don't know if this is relevant or not, but you know, in the early days of MIMO, they used to talk about diversity and multiplexing gain from antennas.
yeah.
So the diversity gain could be the product of the transmit and receive antennas, but the multiplexing. So when you're using some of the antennas as private, so now there is some hit that you take in that. And I'm wondering whether, of course, I realize that this diversity multiplexing is theoretical because it's impractical, I think, in today's world, given the problem of transmit machines. But from a theoretical angle, it seems to me that would you say that the use of private carriers reduces either the multiplexing gain or diversity gain for some subcarriers? That would be a trade-off.
Yes, you're absolutely right. Some antennas, some subcarriers will be used by antennas.
Right.
Actually, no. Even the private, we assign one subcarrier per transmit antennas. So all transmit antennas are used, but some antennas will use fewer subcarriers. So yes, you're right that the multiplexing gain will also change. So we need to look at the trade-off. Thank you.
I have somewhat of a more general question. So for the type of scenarios that you're interested in, such as vehicular communications, while at the same time vehicle safety using the radar aspect of things, I would expect that there would be multi-user interference. And if so, how would you model it? And specifically, more on the radar side, what are some of the challenges in addressing that?
Yes, you're absolutely right. And the radar are very sensitive to interference. The good thing is, with those high frequencies, gigahertz and up range, 24 gigahertz and up, the signal dies out very fast. So the interference will be much less, right? You still have to address it, right? So that's why the pre-coding is very important. You need to design a beam that sort of minimize the interference that you have. So if you have some idea about the interference that you are experiencing, and you can learn what is the cause of clutter in your environment, then you can design that beam to address the interference.
And my guess is that's one area where a lot of physical experimentation is required.
Yes, and now we have these intelligent reflective surfaces that can help us with that, right? You can deploy them on the side of the street or on the car, and this will give you additional degrees of freedom to create beams and avoid interference.
Any other question? Yeah.
Yeah, the question is related to the parameters that you estimate in the radar scene. You talked about the phase of arrival and the range. So you also showed one plot where you said Doppler estimate accuracy also, but you did not talk about the estimation method for the Doppler. Is it again a grid-based estimation method, or is it something different? That is one question. The other question is Doppler estimation important in radar scene estimation in automotive, intelligent transportation systems, or not?
So after you estimate the range, if you look at the peak, the information that gives you the range peak along different OFDM symbols, and you take a DFT, then you'll get peaks that will give you the Doppler information. So it's DFT-based estimation across multiple OFDM symbols.
Okay. If there are no more questions, let's thank the speaker in the usual manner for a wonderful talk. Okay. I'll just ask her if she's. Give a gift to her. You can give the other. Okay. This bag. Okay. We are very happy and fortunate to have the donor, Nirmala, here, who happens to be an alumna of ECE department, 1996 ME batch, and I was her project advisor. So, very happy to. So, may I request you to. One photograph. We thank you for your generous support. Now I'll request Professor Rajesh Sundaresh on behalf of ECE department at IISc. Give a
Thank you very much.
This is about the animals here in the campus. We also have a medallion.
Oh, wow. Thank you so much.
Thank you all. please join us for tea in the adjoining reception hall.